time for one of those items that is just a little bit too big for my bench area and just kind of overspills a bit. So this is a LED baton bar. But the interesting thing is that it's a sort of ultraviolet. When I say ultraviolet, it's near ultraviolet. And it's described on eBay as UV LED bar stage lights, 9 LED 27 watt black tube lamp DJ disco party lighting show. And it was, in the UK, it was £17 inclusive of shipping. And it came through quite quickly. So this thing has a sort of vague brand in it, U-King in the sort of Firefox logo. It's even got an even bigger one under the bottom there. And I've tested this. Let me bring in the hoppy and show you. As usual with these things, they put in these sort of, what the Chinese refer to as beads, 1 watt beads on the, 1 watt or 3 watt beads on eBay. And they often, when you get a light with 9 of them, it will say 3 watt LEDs, 27 watts. In reality, you plug in the hoppy, it lights up in that lovely purpley colour, and it's displaying just over 9 watts. So these are effectively either 3 watt LEDs being run at 1 watt, which is good, or 1 watt LEDs. And the thing about the colour is it's what I'd call near UV. It's not actual UV, but that's fine because the human spectrum goes from being red at one end, it goes right through the peak of spectral sensitivity, which is green in the middle, green and yellow, and then it goes to the blue end of the spectrum. And when you've got fluorescent materials like this, they can be excited by wavelengths that are shorter. So the blue end of the spectrum is shorter wavelengths. It's a sort of higher frequency light, if you will. And it doesn't work the opposite way, which is sad, because it would be nice if lower frequency wavelengths, like, say, for instance, infrared, could stimulate stuff like this, because we'd have had white LEDs a long time ago if that was possible. But in reality, we're stuck with the fact that from the blue spectrum onwards, well, technically speaking, from the green and yellow spectrum onwards, it will stimulate these. But because our eyes can see visual light, visible light, it kind of swamps out the fact they're fluorescing. You can still see, this is why they use it as workwear. It's still very, very bright in normal daylight. But I can show that with a little blue LED wand here. So let's bring in the little blue LED wand, turn it on, and this is just blue LED light, and if I shine it at these, you'll see it really makes them fluoresce brightly. In fact, in the old George Square, this thing's going to peep forever now. In the old George Square Christmas lights, we had ultraviolet active angels, which were big steel angels painted with a white base coat originally, and then ultraviolet colours like these. They looked really stylish. And they were originally lit with actual ultraviolet, 400 watt ultraviolet lamps. They were just a nightmare. They were just, the cases were prone to condensation inside, which then, yeah, that's that light turning off, which then dripped in the glass and shattered the envelopes, and then fortunately, they were pointing up the way, so it didn't really cause a problem. But we latterly swapped them out for just blue metal halides because it just had the same effect. So in this case, although this is near UV, it's not actual UV, it's still at the darker end of the blue spectrum, which means that fluorescent colours fluoresce well. And this thing actually works really well. You point it at in a room, I had some of my high-vis overalls in the corner, it made them really pop. It worked really well. So let's open it, because that's what we want to do. Things worth mentioning. It comes with brackets. Little brackets like this, so you can either use them as stands with this these thumb wheels, or thumb screws, or wing nuts, or whatever you want to call them, wing bolts really, I suppose. So they go in the end, and you've also got a little fan here, which is nice, and the fan is blowing up to this end here, or sucking from this end, not sure which way. So let's open this up. I'm not sure which end to open. Let's open both ends. That's the best bet, isn't it? So I've looked out the correct size of screwdriver, but I have not seen in here yet. I've looked down the end, and I can see that the LEDs themselves are mounted on aluminium plate, and there is a heatsink in the back of it. This bodes quite well for longevity, or longevity, as some people like to say. Is it longevity or longevity? I'm not really sure. Maybe it's one of those cultural things that people in different countries pronounce it different ways. The other possibility with this, if you had a very specialist application, I suppose you could refit it with the LED colour of your choice. What are we seeing here? What are we seeing? We're seeing blobs of hot melt glue. We're seeing, oh, we're seeing this sliding out. We're seeing lots of loose reflectors. That's quite interesting. Oh, they're press fit over the LEDs. Look at that. I like that. One thing to note with these chrome plated reflectors is that they are actually usually coated in metal. Let's test that right now. Let's get the meter in and stick it to continuity and see if they're conductive. It's just something that's worth remembering. I'm not sure which side will be. Yeah, that's conductive. Just remember that these little chrome plastic reflectors are conductive on one side. Are they conductive on the other side? Oh yes, they are. They're conductive on all sides. That's lovely. So there's hot melt glue, liberal hot melt glue at both ends. Is this going to slide out this way? No, it's not going to slide out that way. I'm going to have to take the other end off. Rightio, that's okay. It won't take too long. This is just a bit too big for this bench. It's quite a nice casing in the sense it does have these channels designed to take that aluminium panel with the tracks on it and the LEDs mounted directly onto it. And it does bode quite well for if you warmed this up for replacing the LEDs yourself. I'm guessing that the fan is possibly tapped off across these LEDs, or I could be wrong. Not really sure yet. We'll find out when we open this up. So one more screw to come out the end. Actually, I don't need to take it completely out. I'll take it out anyway. And this slides down this way. Oh, interesting driver. Interesting driver indeed. I wasn't expecting. I was expecting a fairly standard module, but it's got a dedicated output for the fan. What voltage is the fan then? That's odd. Hold on. I think this merits further investigation. I think we'll power it up. Noting that it may or may not be fully electrically isolated. I would hope it is, but you just never know. So let's turn this round to an optimistic value of about 200 volts. And let's plug this in. And then probe about. There's an earth connection onto one of the screws that holds the circuit board in. So let's probe the LED power supply here. So let's bring the meter in where you can see it. Let's probe onto these connections, the LEDs. 9.7 volts. That means it's a 3x3 array, and that is a typical, probably, sort of a 10 watt type driver. And that means the output to the fan will also be about 9 volts, because I bet they're just in parallel. Let's see if I can get the meter into that. The fan's feed, it is 9.8 volts. So this is just I wonder if it's a current regulated supply. It must be current regulated, and they've just got those two circuits in parallel. Oh, actually, you know what? I see the... You know what? I'm going to take this power supply out and we'll take a closer look at it. I'm just going to pause momentarily while I do that. So here's a close-up of the power supply if you want to reverse engineer. I've flipped the image of the back of the circuit board so it correlates exactly to the component positions. So the chip that's being used for this is a DK124. That's swamping out. One moment, please. That's better. And we get the supply coming in and goes through a discrete full bridge rectifier. 33 megafarad, 400 volt. It's actually 10 megafarad, but it doesn't actually matter that much because this is a 24 watt chip and it's only being used about 10 watts. It's really low, less than that. It's being used pretty close to a third of its rating, which makes a refreshing change. We've got the chip it drives its power supply itself, and it's got a little smoothing capacitor for that, just for the chip. It's got a filtering capacitor and an opto-isolator for feedback. It switches the inductor, the transformer, the primary transformer, and it has a snubber network over it with a capacitor to clip the spikes and a resistor in parallel with that to discharge that capacitor, and the diode to divert the spikes and that, so that when the transistor in this turns off, the transient actually goes into this filter and gets suppressed. On the output, we've got a diode and a capacitor. They've not got filtering the output of this. They've not got the inductor and capacitor. And the feedback is just as shown here. Here's the opto-isolator's LED. They've got a 470 ohm resistor and they've got a Zener diode in series with it. In this case, they're showing an 11 volt Zener diode to give which combines with the forward voltage of the infrared LED in the optocoupler to give about 12 volts. But in this case, they're using a different value of Zener to actually limit the voltage. And initially, I have to say, I thought they were relying on the transformer as almost like a current limiting component, but they're not. It is a fixed voltage output, as I'll show you. So here's the bridge rectifier. Here's the smoothing capacitor, which is 10 microfarad. The snubber network is this fairly big resistor. It's a 68K, blue, grey, orange, 6836830, 68K, in parallel with this little capacitor that absorbs those spikes, and then this just keeps that discharged. And there's the diode that diverts those spikes to that snubber network. Here's the little decoupling set of the little filter capacitor, which filters the output back, the signal from the optocoupler. There's a little tiny electrolytic that provides a supply for this, which it seems to be deriving internally. It runs at very low current. There's a fuse. That's nice. I do like the fuse. Is this bright enough? Let's brighten it up. There is a Class Y type capacitor, and it doesn't look, it's not like one of the wee tiny ordinary capacitors. It looks like they've actually chosen a decent specification capacitor. It's also worth noting that they seem to have put in decent separation between the two parts. Goodness knows how good the transformer is. You'd have to unwind that to see, how good it was. You could do a high voltage test, but that doesn't reveal, that only goes so far. As these units age, if there's wires crossing, then the high voltage test may be passed, but over time when the insulation breaks down, it may cause a problem. There's a big fat diode over there, feeding this output smoothing capacitor. And there's the resistor and the Zener diode feeding the input to the optocoupler. Things worthy of note. 2 output connectors. They are both the same polarity. Top is positive, bottom is negative, but they're reversed. So if you take one of these apart, as with all these disco lights, it's a really common thing, the disco lights, that they have one connector one way and one the other way. And it means that when you plug on, if you've got, say, an LED panel to connect onto that, it doesn't matter which way the polarity is in that, you can plug it into the right connector, but it means if you get the wrong connector, it can damage the circuit boards. One of these is feeding the fan. If you plug the fan from this one into this one, it would put reverse voltage across the fan. It could damage it, because this can source a decent bit of current. So I don't know why they do that, but it is quite common. The answer there is, if you take your disco light to bits, take a photo. This shows a little switch. There is a connector here and a connector position here. That connector connects to a switch. Basically, it switches this connector here on and off. There are other component positions for what I'd guess is a 431 voltage reference, and then a set of resistors. These 2 resistors here in parallel and in series this one, which would set an accurate voltage reference in that as an alternative to the Zener diode to give, if you wanted to have a very, very accurate voltage reference. And that is more or less it. I mean, I say more or less it, it's actually quite good. It's a unstressed power supply, which is nice. Talking of which, hot components. This resistor was the hottest component. It was 30 degrees above ambient, which is nothing, 30 degrees Celsius. The chip was running at 20 degrees Celsius above ambient, which is nothing, and this diode was running at 30 degrees Celsius above ambient, which was nothing again. I left the LEDs running for a while with the heatsink, with the fan not really diverting air across the heatsink. It's a big panel. I mean, seriously, look at the back of it. It's got that big fat heatsink in the back as well. I don't think I mentioned that before. It has this. It's only held on 2 screws, but it's a worthy thing. But the dissipation of the LEDs is about 20 watts. Nothing. 20, not 20 watts. 20 degrees Celsius above ambient when I'd left it for a while. I don't know what that is. That sort of stuff. Ugh. Manufacturing schmoo. The supply comes on here, and the LEDs are wired. There's a sort of a positive bus bar goes along the bottom, and the negative loops round and it goes along the top, and then it comes down, goes through this LED, big heatsink area. You can't see it because it's black. Oh, you can actually kind of see it. Can you see the big huge pads? So it really is a huge rectangle. They've used all the space. They've even got a coupler underneath the LEDs themselves, even though the LEDs are only being run at 1 watt. So these LEDs, 1, 2, 3, are in series, and then it kicks over to this bus bar. Next, top bus bar comes down, 3 in series. So it's just 3 in series, 3 in series, 3 in series, all in parallel. The circuit board says LED UV 9 pieces, so it's dedicated to this task. It's also got a date, 26th of the 6th, 2017. Weird. It's all running completely within sensible levels. That's quite odd. I have to say, some of the disco light and stuff is pretty impressive. It still has that slight element, though, stuff with DMX, of the risk that it could pat 240 back onto the DMX network, but other than that, it's not bad. Well, that is quite bad, actually. So the fan is now running. The power supply is powered up here. The case is earthed. That's also nice. Let's bring the meter in and show that even with the LEDs off, this is set to 20 volts. Let's probe across there and see that it's still at 9.9 volts-ish. That means that they're basically capping the current through the LEDs by setting the voltage across them. It's quite an odd way of doing things, but it's reasonable enough because they're controlling that quite accurately. I shall unplug this before I stick my fingers in there and scream like a pig. So what can I say? It's a nicely made light. It's not running the LEDs too hard. If you wanted to replace the LEDs in this, you could. I think to do that, you'd want to warm up this panel before you started trying to solder, desolder LEDs, because this aluminium panel is going to take a lot of heat away from them. You could pop the heatsink off with just these 2 screws. Let's do that. Let's pop that heatsink off. I bet there's no heatsink compound on it, but I could be wrong. Let's see if it proves me wrong again. We'll whip those 2 screws out. I don't think it actually needs heatsink compound. It's just, there's no heatsink compound. But if you wanted to replace LEDs, I think you'd have to replace all 9 so they all matched with voltage-wise. But you could heat this panel up, maybe in sections on a sort of like, well, the inverted iron approach, and then you could solder new LEDs in. And because these reflectors, because they actually clip onto the LEDs themselves, that wouldn't, the alignment wouldn't be too critical. I suppose technically speaking, you could just leave the front plastic off this. It's not that needed. Then again, that would mean all the reflectors pop out the front. But they go on quite tightly. Yeah, you know what? Overall, it's quite nicely made. It's functionally designed. The power supply is being well underrun. The LEDs are being, what I'd say, underrun. They've got loads of heat sinking. There's a fan to keep it cool. Everything seems to be really good. That is so strange. And it does pack out a relative punch of UV style light, that deep violet, which is quite nice in its own right. Yeah, it's a win really, isn't it? Can I say anything bad about it? Not really. I don't even know if that heatsink there is actually 100% needed, given the dissipation and the fact it's fan cooled. Maybe they were just allowing with the fact that by bumping the voltage up a little bit, by changing this zener, then you could actually push these LEDs up to a much higher power, but you'd have to be careful. You'd have to experiment with that. Even 0.6 of a volt, like suppose you put a standard diode in series with that. But in reverse series, should I say, then that would nudge it by 0.6 volts. That could have quite a profound effect in the current through the LEDs. But it's very interesting, quite nicely made, quite a pleasing little light. Oh, I should mention that before MD mentions that the drawing, where is I've just lost the other image I had. If you look at the other pictures anyway, you'll see that it looks like there's a dry solder joint. It's not. That pad isn't used. It's just actually a reflection of the setup I used to take pictures of these, which you can see a little arc of LEDs going around there. Yeah, it's actually quite a nice little light.